Hello everyone, and welcome to Lesson 3 of Waveshare's ESP32 Arduino Getting Started tutorial. In the previous lesson, we successfully made the ESP32 print Hello World to the computer via the serial port. Now, it's time for our ESP32 to step out of the screen and make a real-world impact. In this lesson, we will move beyond the computer screen and enable the ESP32 to interact with the physical world. We will learn two of the most fundamental and essential skills. Digital output. We will use code to light up an LED. Digital input. We will build a simple circuit to let the ESP32 detect whether a button is pressed. The key to understanding all of this lies in grasping the concept of digital signals. First, let's discuss what a digital signal is. In professional terms, a digital signal is a type of signal that uses discrete, non-continuous values to represent information. In the world of electronics, the most common digital signal is a binary signal, which has only two distinct states, much like a light switch in a room, either on or off. These two states are referred to as high level and low level. In the world of the ESP32, high level represents a logical one or true. On the ESP32, this corresponds to a voltage of approximately 3.3 volt. Low level represents a logical 0 or false, corresponding to a voltage of approximately 0 volt. In simple terms, digital signals use these two voltage states to convey information like high and low, or 1 and 0. So, how does the ESP32 handle these signals through its pins? The answer is GPIO. GPIO stands for General Purpose Input-Output Pins. On the ESP32 S30 development board in your hand, the numbered pins along the edge are GPIO pins. They serve as the bridge for the ESP32 to interact with the external world. Regarding digital signals, you can consider almost any pin on the ESP32 as a digital pin capable of handling digital signals. As a digital pin, it operates in two modes. Output mode. When set to output mode, the ESP32 is like talking. It actively controls a pin to output a high level or low level to command an external device, for example, turning an LED on or off. Input mode. When set to input mode, the ESP32 is like listening. It detects whether a pin is at a high or low level to understand what is happening in the external world. For example, whether a button is pressed. With this understanding, we can now start hands-on practice. Let's begin with output, making the ESP32 output a digital signal to control an LED. First, we need to build an LED circuit. To build this circuit, you will need an ESP32 development board, a breadboard, an LED, a resistor around 330 ohms, and several jumper wires. Before we start connecting components, let's first understand the principle of this circuit. For the LED to light up, we need to create a complete current loop. Current flows out from a GPIO pin on the ESP32. This pin acts as the positive terminal of the power supply. The current then passes through a current-limiting resistor, flows through the LED, and finally returns via the ESP32's GND pin, forming a closed loop. In this circuit, the ESP32's GPIO pin acts as a smart power switch. When it outputs a high level, it is equivalent to closing the switch, supplying 3.3 volt from the pin and lighting up the LED. When it outputs a low level, it is equivalent to opening the switch, supplying 0 volts from the pin, and turning off the LED. Now that we understand the principle, let's get to know a very practical tool for building circuits, the breadboard. It allows you to quickly assemble and modify circuits without any soldering. Central area. Each vertical column of 5 holes is internally connected. Please note that the central groove separates the left and right sides. Side power rails, typically used for connecting power and ground. Each entire horizontal row is connected. If it's hard to remember at first, you can take a screenshot of this diagram. Each highlighted section that is connected together represents a conductive path. As you become more proficient, you'll gradually rely less on this reference. Now, please follow the wiring diagram shown on the screen to make the connections. Step 1. Securely insert the ESP32 development board into the center of the breadboard, ensuring the pins on both sides are separated by the central groove. Step 2. Take out the LED. You'll notice one leg is longer than the other. The longer leg is the positive side, and the shorter one is the negative side. Insert the LED into the breadboard, paying attention to the direction of the longer leg. Step 3. Connect one end of the 330 ohm resistor to the same vertical column as the LED's positive leg. Connect the other end of the resistor to any empty row on the breadboard. Step 4. Use a jumper wire to connect the free end of the resistor to GPIO pin 7 on the ESP32. Step 5. Use another jumper wire to connect the vertical column containing the LED's negative leg to a GND pin on the ESP32. If you don't have a 330 ohm resistor on hand, using one within the range of 220 ohms to 1 kiloohm is generally acceptable, though the LED brightness will vary slightly. The circuit is now assembled. Now, let's bring it to life. Open the Arduino IDE and copy the provided code into it. You can find the link to this code in the description below the video. Select the corresponding development board and port number, then click the Upload button. Once the upload is successful, you will see the LED start blinking in a regular pattern. Congratulations! You have successfully completed a landmark step in hardware programming, lighting up an LED. Next, let's go through the code line by line to understand how it works. Before any functions, we define a constant named LED pin and assign it the value 7. In Arduino programming, it's a good practice to use camel case for naming variables, starting with a lowercase letter and capitalizing the first letter of each subsequent word. Defining the pin number as a meaningful variable name has two major benefits. It improves code readability, and if you later decide to move the LED to a different pin, you only need to change this single line, making the code much easier to maintain. Now, let's look at the setup function. Remember, the code here runs only once at startup, typically used for initial configuration. Before using the pin to light up the LED, we need to initialize it first. The pin mode function is used to set the operating mode of a pin. It has two parameters. The first is the pin number, which we use here as LED pin variable. The second is the mode, where output is a predefined constant representing the output mode. If you're interested, you can right-click on Output and select Go to Definition to view the value of this constant. We don't need to memorize this value, just knowing it exists is enough. Predefined values like these make Arduino code easier to write and more readable. The purpose of this line of code is to tell the ESP32, set the pin connected to the LED, that is, pin 7, to output mode. The ESP32 will then handle the corresponding preparations. Next, let's look at the loop function. The code here runs in an infinite loop, digitalWrite, as it literally means. This function is used to write a digital signal to a pin that has been set to output mode. Open the official documentation and search for digitalWrite. Let's look at its description. Writes a high or low value to a digital pin. If the pin has been configured as output via pin mode, its voltage will be set to the corresponding value. High is 5 volt and low is 0 volt. We see that digitalWrite has two parameters. One is the pin number and the other is the level value. High and low are also predefined constants in Arduino. When executing this line of code, the ESP32 will output a high level on pin 7, which is approximately 3.3 volt, thereby conducting current to light up the LED. By the way, in the underlying Arduino code, high and low are actually predefined as 1 and 0, respectively. So writing digitalWrite LED pin 1 here would achieve the same effect. However, for code readability and standardization, we strongly recommend always using high and low. This line of code is familiar to us. It pauses the program for 1,000 milliseconds. During this second, the pin state remains unchanged, so the LED stays lit. Next, we call digitalWrite again, but this time the second parameter is low. The ESP32 will immediately switch the voltage on pin 7 to a low level, i.e. 0 volt. The circuit is cut off, and the LED turns off accordingly. Finally, pause for another second to keep the LED off for 1 full second. When the loop function reaches its end, it doesn't stop, it immediately returns to the beginning and executes digitalWrite again. Repeating this process creates the rhythmic 1 second on, 1 second off blinking effect we observe. Now, to reinforce what you've just learned, I've prepared two small challenges for you. You can try either one or both. The first challenge is to try lighting the LED with another pin. Remember, after changing the hardware wiring, the LED pin constant in your code must also be updated accordingly. The second challenge is to modify the values of the two delay in the code. First, reduce them, for example, to 200, and observe how the LED's blinking changes. Then, try to find the threshold, the point below which the blinking becomes indistinguishable to the naked eye. This is actually a classic test in the Arduino community, where many people are curious about their own visual limit. Try to see what your threshold is. Now, you can pause the video and try it out. Welcome back. Did you succeed in the challenge? Feel free to share your experience in the comments section.